This is the third and final section of the integration technique chapter, and here we're going to be looking at the surface area of revolution. Now, we've previously looked at finding the length of an arc, the part of a curve. Now, if this is rotated 360 degrees around the x or the y-axis, then we create this like hollow shape, a surface. Okay, unlike a volume of revolution where it's completely filled, here we're just talking about a hollow shape. So imagine like a paper tube or something like that, and we're working out the area of the surface. So we, just like we've got formulas that we can use for arc length, we've got formulas that we can use for the surface of revolution, that area, and the ones highlighted in yellow are the ones in the formula book. Okay, the ones not in yellow are not in the formula book. So if we have a Cartesian equation of the form y equals f of x, then this is the form that we use. If we have a Cartesian equation in the form x equals f of y, so it's swapped around, we can use one of these two forms depending on which axis we're rotating around, the x-axis or the y-axis. But these are not given in the formula book, so but we can use these to get these. If we have a parametric equation, then we can use this form if it's rotated around the x-axis, this form if it's rotated around the y-axis. So this one around the y-axis is not given in the formula book, but you can see it's easy to derive. We just swap that x with y, and if we've got a polar equation, then this one's given in the formula book. This will give us a surface of revolution rotated around the x-axis, this one around the y-axis, but this one is not given in the formula book. But it's easy to derive because you can see the only thing that's different is sine becomes cos. So make sure you're aware of how to get these ones which are not in the formula book and how to derive those from the ones highlighted in yellow which are given in the formula book. Okay, so the first thing we need to do in this question is decide what type of graph it is and whether it's rotated around the x or the y-axis. It's Cartesian, it's rotated around the y-axis, so then we can pick out the appropriate formula to use. Now notice that we use capital S to stand for surface area and lowercase s to stand for arc length, but this is the formula that we'll use to find the arc length. We can get this one straight from the formula book. So we'll start first of all by working out what dy dx is. Now we have y equal to 1/3 root x times by 3 minus x. So we've got to expand the brackets first. So we'll have y equals root x, or x to the power half, minus 1/3, so that'll be x to the power half plus 1, x to the power 3 over 2. Okay, let's now work out what dy dx is. So that will give us half x to the minus a half, and then what have we got? 1/3 minus 1/3 times by 3 over 2, which is actually a half, so minus a half, x to the power a half. Okay, so now we're going to work out dy dx all squared. So that's going to be this half x to the minus a half minus half x to the half times itself. Right, so multiplying that out, that'll give us a quarter x to the minus 1 minus a half x plus a quarter, sorry, just minus a half plus a quarter x. Now let's try and do as much as we can before we put it in here. So let's add the 1 to this dy dx all squared. So add 1. And then what we end up with is a quarter x to the minus a half, minus 1 plus a half plus a quarter x. Now we know we're going to be square rooting this, So really we want to be able to write this in a form where we can square root it easily. I'm not going to be able to square root it written like that. So let's take a quarter out as a factor, leaving us with x to the minus 1 plus 2 plus x. And then what will happen is that the bit in the bracket will actually factorise to x to the minus a half plus x to the half. You can expand it and check all squared. So now what we've got is our surface area of revolution is going to be 2 pi times by, now my limits are here somewhere, here we go, 1 and 3, so we'll put those in, times by y, and y is this, so we'll write our expanded form, x to the half minus a third x to the 3 over 2 times by the square root of what we factorised, which was half x to the minus 1, x to the minus a half plus x to the half all squared, and then there's meant to be a dx there at the end. Right, we can simplify that because obviously the square and the square root are going to cancel out, and this quarter will become a half. Then the 2 and the half are going to cancel out, so we can simplify and just have our surface area revolution equal to just pi, that's divided by the half. There's our limits, and then what we're left to do is to multiply out these two sets of brackets here. So x to the half minus 1/3 x to the 3 over 2 times by x to the minus a half plus x to the half. So lots of little powers and things that we need to be careful of when we're multiplying out. Right, now if we do multiply it out and simplify it, we'll be left with this 1 plus 2/3 x minus 1/3 x squared. And then we are now ready to integrate that. So we'll integrate each term. So obviously the 1 becomes x, the 2/3 x, so then we're going to have 2/3 divided by 2, so it just becomes 1/3 x squared. Then the next term, that will be 3, and then we'll divide by 3, so it becomes minus a 9th x cubed with our limits of 1 and 3. Okay, so this is what it will be once we've substituted in the values of 3 and 1. If we work that out, then the first bracket times by pi will give us 3 pi. The second bracket times by pi will give us 11 over 9 pi, giving us a final surface of revolution of 16 over 9 pi. So we'll just highlight that. Okay, so the first thing to note that this is a curve with a parametric equation and it's rotated about the x-axis, so we need to pick the correct formula to use. So this is one that we can use, get it straight from the formula booklet. Because we've got some trig here, there may be points where we need to use some trig identities, so we'll just keep that in mind as we go along. Right, so we've got x equals t minus sine t, so that means that the x dt is going to be 1 minus cos t, and we have y equals 1 minus cos t, so that means that dy dt is equal to negative sine t. Sorry, not negative sine t, just sine t, because it reverses sine, doesn't it? Right, so we want to know what we get when we square our derivatives and add them together. So let's write down what that's going to be. Right, so it will be 1 minus cos t all squared plus sine all squared. Right, so if we expand the brackets, we'll get 1 minus 2 cos t plus cos squared t plus sine squared t. Well, I can see straight away, here's my first identity. I can replace that with 1. So this becomes 1 plus 1, so it's 2 minus 2 cos t. Right, so if I substitute in what I've got so far, the limits I have, which are here, 0 and 2 pi, so I'll put those in. And then we're going to have y, which is 1 minus cos t, and that's going to get multiplied by the square root of 2 minus 2 cos t. Now the problem is, I can see a problem already, I can't square root this, so I'm going to have to use a trig identity. And I'm going to use this trig identity. So if I say cos t rather than cos 2t, that's going to be equivalent to 1 minus 2 sine squared t over 2, which means then I can substitute this cos t for this here. So let's do that and see what we get. So s equals 2 pi, same limits, 1 minus cos t, and then it's going to be the square root of 2 minus 2, and then times by 1 minus 2 sine squared t over 2. Now what will happen when I expand these brackets here, because I'll get 2 minus 2, so that's gone, and then I'll get 4 sine squared t over 2. So because this here, all of that will become 4 sine squared t over 2, and I'm going to square root it. Square rooted, it will become, and I've noticed I need another bracket here, it will become 2 sine t over 2. So this is what it will become in the next step. So s equals 2 pi, then 0, 2 pi, and we've got 1 minus cos t, and that will get times by 2 sine t over 2 dt. Okay, another trig identity. So I've got 1 minus cos t here. Now actually 1 minus cos t is going to be 2 sine squared t over 2, so let's just write that down. That 1 minus cos t is equal to 2 sine squared t over 2. That's handy because that will give me the same term here and here. And then if I multiply that out, that will give me 4, won't it? So 4 sine cubed t over 2 dt. Right, in the next step we're going to move this 4 over because it's a constant. So now we have 8 pi as our constant, and then we need to think about how we're going to differentiate this sine cubed. Well, if we write it as it's meant to be an s there, so yeah, if we write it as sine squared times by sine, so sine squared t over 2 times by sine t over 2, like this, then use another substitution. So we can say that sine squared t over 2 is equal to 1 minus cos squared t over 2, like this. Then we're going to substitute that here, and then we're going to be able to use substitution to be able to do the integration. So 8 pi, 0 2 pi, and then we'll have 1 minus cos squared t over 2 t over 2 times by sine t over 2 dt. Okay, right, now we're going to use substitution. We're going to let u equal to cos t over 2, which means that du dx will be equal to negative a half sine t over 2, which means we can replace dx with du divided by negative a half sine t over 2. And actually dividing by negative a half is the same as multiplying by 2, so maybe when I move it I'll put times by negative 2 instead. And then since we're doing a substitution, we need to substitute the limits. So we have at the moment t limits, which we need to change to u limits. So my t limits are 0 and 2 pi. To find out what the u limits are, I will need to put the values of t in here. So when t is 0, I get cos 0, which is 1. When t is 2 pi, this becomes cos pi, which is negative 1. So my two limits are going to be 1 and negative 1. So let's now make all of the substitutions. So s equals 8 pi times by, so we change the limits as well. The lower one is 1, the upper one is negative 1. 1 minus cos squared t over 2 becomes 1 minus u squared. And the sine t over 2 is not gone yet, but it will go in a minute when I substitute in my dt. Right now, just notice I've used dx here. They should be t's. So dt, dt, sorry about that. So yeah, swap dt for this. So du over, and we'll stick the minus half down here for the moment. Sine t over 2, like this. So what's going to happen? Well, this will cancel out, which is handy. And then I've now got this divided by negative a half, which is times by negative 2. Let's move that over as well. So now I'm going to have negative 16 pi, negative 1 and 1, and just 1 minus u squared du. Right, now that's easy enough to integrate. So not forgetting my negative 16 pi. The 1 will become u. The u squared will become 1/3 u cubed. And I just need to plug in my limits now, negative 1 and 1. Okay, so when we put our limits in, when we put negative 1, we get negative 2/3, minus when we put 1 in, we get 2/3. So we've got negative 4 over 3 times by negative 16, and that will give us 64 pi over 3 as our final surface area. Okay, so just like the previous ones, we need to decide what equation we're going to use. So this is a polar equation, this one. Now this one is rotated about this vertical line, like the y-axis. So it's rotated this way, not this way. The one in the formula book is for those rotated around the initial line, which has sine in it. To convert it to the one that's rotated around this axis, we just change where we see sine to cos. Okay, so this is the formula that we're going to use. Right, so let's start with what we've been given r. Now we need to find dr d theta, then we're going to square it. So let's find dr d theta first. So that will just be 4 cos theta. So squaring that, dr d theta squared is going to be 16 cos squared theta. Now we also need r squared in there as well. So while we're here, while we're at it, might as well work out what r squared is. So it's going to be this times itself. So that'll be 16 plus 32 sine theta plus 16 sine squared theta. Okay, so now we're going to put all of these into our formula. So s equals 2 pi. Now I can see my limits here from negative pi over 2 to pi over 2. Then I've got r times by cos theta. So r is this 4 plus 4 sine theta times by cos theta. If it was rotated around the initial line, then this would be sine theta here. That'd be the only difference. And then it's the square root of r squared. So r squared we've got here 16 plus 32 sine theta plus 16 squared sine theta plus the derivative squared, which is plus 16 cos squared theta, all defeated. Now it looks very long, but well, these two, that's just going to make 16 lots of sine squared cos squared, so this is going to become 16. The 16 and the 16 will go together, so I'll get 32 plus 32 sine theta. Okay, so what I've done is I've simplified this part here, 16 plus the 16, and I've taken the 4 out as a factor of this. Now what I want to do is to take out as many factors as possible, put them to the other side. Now this here, I could take out 32 as a factor, so I could write this as 1 plus sine theta, like this. And then if I square root that, I'll get the square root of 1 plus sine theta and root 32. Now the root 32 I'm going to take across as a factor as well. So I'm going to have the 4 there over that side and the root 32. Okay, so you should now see in this next step here, I've taken the root 32 out as a factor, and now I'm just left with this. Now I'm going to use substitution. I'm going to let u equal 1 plus sine theta, which means that du d theta is going to equal to cos theta, and I'm going to change my limits as well. So I'm changing my my theta limits, to u limits. So I'm going from theta to u. My limits are negative pi over 2 and pi over 2. So let's start with the first one. So if I put negative pi over 2 into here, that will give me 0. And then if I put sine of pi over 2 into here, that will give me 2. Right, so let's make all of these substitutions. So s, keep wanting to do an interval sign. S is, so we've got 8 root 32 pi. Now with limits of 0 and 2, and the first bracket here becomes u. Then we've still got the cos theta, but that's going to cancel out in a moment. Then this is going to be the square root of u, or u to the power half. Then the d theta, if we rearrange this, so d theta is going to be du over cos theta, so times du over cos theta. So you can see this will cancel out, and then we've got a nice easy integration because all of this just becomes u to the power of 3 over 2. So we can probably go straight now to our integration. So 8 root 32 pi, and as I said, this here just becomes u to the power of 3 over 2. So that will become, when it's integrated, 2/5 u to the power 5 over 2 between our limits of 0 and 2. So working that out on our calculator, obviously when we substitute 0 in, there's not going to be anything. So it's basically 8√32 pi times by 2/5 times by 2 to the power 5/2, and that gives us 512 pi over 5. So I'll just highlight that there as our final solution. Okay, so looking through this question, I can see that I've got a Cartesian equation that's been rotated completely around the y-axis. So I need to choose the appropriate formula now. The one for rotating about the x-axis is in the formula book. So all you need to do is take that one and swap over the x and y's, and you will get the correct formula to use. Okay, so this is the formula we're going to use. As I said, it's not in the formula book, but if you look for the formula where you're rotating around the x-axis, which is given, the only thing that changes is the x that was here changes to y. Okay, so we've got y equals cosh h. So we need to find dy dx, and when we differentiate cos x, we get sin x. Now notice that we have x limits here. Even though it's rotated around the y-axis, it's just easier to use this form. So that means that we need to swap in these values here, 0 and log 2. So let's do that. And what we'll have is the surface area of revolution is 2 pi, limits of 0 and log 2, and then x times by the square root of 1 plus sin squared x dx. Now we'll use our hyperbolic identity here, and that's cos squared minus sin squared is 1. So if we swap or rearrange this, so then we'll have that sin squared x is equal to cos squared x minus 1. So that's going to get slotted in here. So when I put in cos squared x minus 1, well, that one's going to go, and I'm just going to be left with cos squared x. Now it makes sense that, well, I'm going to be square rooting it, aren't I? So because I'm going to end up with cos squared x there, and I square root it, what we'll end up with just x times by cos x dx. Now, something of this form, we would use integration by parts. So using integration by parts, we'll have u equal to x, as we normally do. So I'll have du dx equals 1. Then we will have dv dx equal to cos x. So if we integrate that to find v, that will be sin x. So yeah, just putting those things now into the integral. So it's going to be 2 pi times by, well, it's going to be uv, isn't it? So u times by v, which is x sin x, between those limits of 0 and 2 pi, sorry, log 2, minus the integral of v du dx, which is just sin x dx, again between 0 and log 2. So I should have some big brackets around the whole lot, because everything's going to get times by 2 pi. Right, so we're almost there. So what are we going to have? Well, I'll do the substitution for the first part. So log 2 sin log 2 minus 0 times by sin 0. So I didn't really need that part because that's going to end up as 0 anyway. Okay, so that's the first part. Then I need to integrate this. So shine integrated is going to be cosh, and it's going to be cosh x between these limits of 0 and log 2. Right, so we can finish this off. Okay, so when we work this out, and we can actually do it on our calculator, shine of log 2 on a calculator comes out as 3/4. And then when we work this bit out here, we'll have cosh of log 2. So cosh log 2 minus cosh 0. So the cosh of log 2 on a calculator comes out as 5/4, and the cosh of 0 comes out as 1. So let's write down what all of this is going to be. So everything's going to get multiplied by 2 pi, but in the brackets we're going to have log 2. That's going to get multiplied by 3/4, which is the shine log 2, minus nothing. And then we're going to subtract from that cosh log 2, which is 5/4, minus cosh 0, which is 1. Okay, the rest is just tidying up the maths really. So I'd probably want to put the 3/4 in front of log 2, or I could write log 2 to the power 3/4. I'll leave it like that. Then we're going to be taking away 1/4. Now it's fine to leave your answer like that, or you might decide, right, let's take this 1/4 out as a factor, which means dividing this by 4. 2 pi divided by 4 is going to be pi over 2. And then we take that 1/4 out, and then we're just left with 3 log 2, or log 2 cubed, log 8, minus 1. So it all depends on the question. If, like, they say they want it in a certain format, like this, then you would go on to do it in this form. If not, just leave it as it was here in this previous one. Okay, so you should now be able to do exercise 6C on pages 210 to 212. So just a quick recap of what we've done with this surface area of revolution. So anything that's highlighted in yellow is in the formula book. The little diagrams here indicate whether the formula represents rotating around the x-axis or y-axis. The first set here are for Cartesian equations, so pick out the one that's most appropriate. The second set here represent where we have parametric equations, so again pick the one that's most appropriate. And the last set here are for our polar equations. Okay, now just be aware that some of the integrations that you may need to do may be quite tricky, so you need to be really well versed in your integration methods from Pure 2 and from Core 2.